Hello people, today we want to study the application of Fourier analysis in radio interferometry. Here we have an image showing the black hole M87 asterisk at the core of Messier 87. Messier 87, which is generally abbreviated to M87, is a supergiant galaxy with about 1 trillion stars. The black hole was imaged using the data collected by the Event Horizon Telescope. This week, we will learn how astronomers took advantage of Fourier analysis to construct such a news-making image from the sky. Before going to the technical details, I want to give you some further information about the black hole. M87 asterisk weighs in at about 6 billion solar mass, but its event horizon is only about 40 billion kilometers across. The solar mass is a standard unit of mass in astronomy, where one solar mass is equal to approximately 2 times 10 to the power of 30 kilogram. In addition, an event horizon in astrophysics is defined as a boundary beyond which events cannot affect an observer. In terms of distance, the M87 galaxy is around 500 billion far away from the Earth. With these statistics, one might ask how it is possible to take high-resolution images from such a supermassive and far away target. To answer this question, I should say that the Event Horizon Telescope has been used to create images from the black hole M87 asterisk. As illustrated in this slide, the Event Horizon is a telescope that links a large array of radio receivers from the South Pole to the America and Europe. This telescope combines the observations from the dispersed network of the radio receivers to mimic a telescope aperture that can produce the resolution necessary to perceive a pinprick on the sky. But the question is how we can reconstruct a high-quality image based on the data collected from many independent radio antennas. Please follow today's lecture if you want to know the answer to this interesting question. Before studying sky image reconstruction, I want to briefly give you some further information about the principles of telescopes. Scientists require high-resolution telescopes to observe objects in the sky. Angular resolution describes the ability of any image-forming device, such as a camera or radio telescope, to distinguish small details of an object. So, angular resolution is a major determinant of image resolution. As anticipated, the higher the angular resolution, the higher the image resolution. Here we have a formula estimating the resolution of a telescope. In this formula, R represents the resolution in radians. Lambda determines the wavelengths of the observed radiations or light. And D is the aperture or diameter of the telescope. For instance, in visible light, at the wavelengths near 500 nanometer, the combination of the Hubble telescope with its highest resolution cameras achieve an angular resolution of about 0.05 arc seconds. It's interesting to note that the human eye can resolve objects separated by about 40 arc seconds. So, the resolution of the Hubble telescope exceeds that of the human eye by about a factor of 1000. In physics, we studied the fundamentals of light and image formation for parabolic mirrors and lenses. Similarly, traditional radio telescopes use the fundamentals of light to help us see faraway objects. In other words, large steel dishes in this type of telescopes collect weak radio light waves, amplify the waves, and make the results available for constructing the image from the sky. But as mentioned earlier, there are modern radio telescopes like the Event Horizon, consisting of a network of radio telescopes at remote locations. Now, the question is how images are constructed from such a large array of multiple global radio telescopes. To get a feeling for this, let's consider LOFAR, a radio telescope with simpler radio receivers compared with the Event Horizon telescope. The LOFAR radio telescope uses large baseline stations on the Earth, including tens of thousands of fixed antennas. We can see one of these omnidirectional antennas in this image. Using such a wide baseline array of antennas, the LOFAR, unlike traditional telescopes, can observe in hundreds of directions simultaneously and collect signals. LOFAR considers itself as a software telescope. It digitalizes the electronic signals received by the antennas. Then the raw signals are transported to a central digital processor and combined in software in order to make the sky. In other words, LOFAR uses software to process signals received from the global network of antennas. In the following slides, we will study how LOFAR creates sky images by analyzing and combining signals received from a large array of antennas. LOFAR receives electromagnetic waves from the sky to shape a digitalized signal. In each station, the antennas are distributed across a field. Therefore, signals emitted by a source reach different antennas at different times. For instance, in this image, the antenna on the left receives a particular wave sooner than the right one. So, this delay makes signals unaligned. To address this problem, a carefully calculated delay is inserted into all signals received from a desired source before signals from different antennas are combined. This way, all signals from one particular direction are in phase and aligned with one another. In the same manner, the LOFAR subsequently processes the signals from different stations to finally create a sky image. In the next step, the aligned signals are used to obtain the visibilities between antennas. To create a sky image, we need to correlate the signals received from antennas at different geographically separate locations. For instance, here we have a baseline field including two antennas, say P1 and P2. We define a complex function called visibility. A visibility function formulates the correlation between the signals arriving at any pair of antennas. In the following slide, I will explain how we can obtain the visibilities between antennas. In this slide, we can find the steps to obtain the complex visibility between two antennas. First, we multiply together the two signals received by two antennas at corresponding times. Then, we average the result over some fixed interval of time to obtain the cosine correlator RC as a single number. After that, one of the signals is shifted by 90 degrees. Then, similar to the previous step, the two signals are multiplied together. The average of the result over a fixed interval of time is a single number called the sign correlator Rs. The complex complexity V is equal to Rc minus I Rs. Here in this slide, we have the signals received by two antennas. To obtain the visibility correlation between the two antennas, we first multiply the signals together at corresponding times. The result is a new signal. By applying an average on the result, we obtain a single number which is the cosine correlator Rc. In the next step, after shifting the second signal by 90 degrees, we multiply the two signals. By applying an average on the result, we obtain another single number which is the sign correlator Rs. As mentioned in slide 12, the visibility number between antennas 1 and 2 is equal to Rc minus I Rs. Now I want to introduce sky intensity or sky brightness. The sky intensity is the quantity that we usually measure with telescopes. In simple words, the sky intensity corresponds to the strength of lights received by the antennas from the sky. Suppose the point L, M illustrates the position of an object in the sky in an x-y Cartesian coordinate system. Here on the ground, consider a baseline station with two antennas, P1 and P2, located in the x and y Cartesian coordinate system. It is supposed that these two Cartesian coordinate systems are parallel with the same origins. I, L, M formulates the radio intensity of the object observing by the antennas as a function of position on the sky. This function is called the sky intensity. It is important to note that the sky intensity determines the image of a target object in the sky. Now it's time to introduce the Van Sittert-Zernike theorem. This theorem defines the relation between antenna visibilities and the sky intensity of an object in the sky. Suppose U and V are respectively the x distance and the y distance between the two antennas P1 and P2 in unit of wavelengths. As illustrated here, we can find U and V values for any pair of antennas using these two equations. In these equations, xp1 and yp1 correspond to the coordination of the antenna P1. And similarly, the pair xp2 and yp2 represent the position of the antenna P2. Lambda is equal to the wavelengths of the signal received by the antennas. This series here represents the Van Sittert-Zernike theorem, formulating the visibility between two antennas as a function of sky intensity I, L, M. As mentioned earlier, the sky intensity function determines the image of a target object in the sky. In real applications, we are looking for the intensity function I, L, M, not the visibility function. So, we need a series giving us the intensity function based on the signal received by the antennas. After comparing this series with the 2D Fourier transform formulation, we can recognize that the complex visibility between two antennas is equal to the Fourier transform of the sky intensity function. It is an interesting finding, isn't it? So, to create an image of a target object using the signals captured by a telescope, we need to apply an inverse 2D FFT to the visibility function V, including an infinite number of U and V points as shown here. In this series, the visibility function V is determined by the signals received by the fixed antennas. By the way, the values for U and V can be calculated using the positions of the antennas and wavelengths of signals as explained in the previous slide. To create an image using the series in slide 17, it is necessary to measure the visibility function for all possible U and V points. In fact, good image quality requires a broad set of U and V samples. We know that the number of U and V points depends on the number of antennas. Because there is a very limited number of antennas fixed at various locations on the Earth, making full sampling of all U and V points is impossible. In the following slides, I will explain this matter by example. This slide shows a possible physical layout of 27 antennas. The red spots here represent antennas, and antenna names are written adjacent to them. This plot here presents the coverage of UV plane. The plot shows all points in UV plane resulting from all possible pairs of the 27 antennas. The horizontal axis corresponds to U, and the vertical one shows values for V. The values of U and V have been calculated using the formulas presented in slide 16. In this example, the wavelength lambda is considered to be 7.5 cm. As we can see here, because of the limited number of antennas, UV plane is almost sparse. But we require a larger set of U and V points to reconstruct good quality images. The visibility function V can be measured on a discrete number of points. As mentioned earlier, a good image quality requires a good coverage of the UV plane. To create a better quality image, we can exploit the rotation of the Earth to increase UV samples. In other words, although the antennas are fixed, the ground is rotating with the Earth, and therefore the antennas are rotating with respect to the fixed stars. So we can obtain further U and V samples by repeating measurements and observations many times throughout the day. This plot shows the UV coverage of the previous example, including 27 antennas. To increase the coverage, the observation has been conducted for over 5 hours. It can be seen that a longer observation results in more UV samples due to the Earth's rotation. Now we can obtain an approximation of the intensity function I as shown here. In this sum, we use sample points in the UV plane. The sky example estimated by this series is technically known as the dirty image. As mentioned earlier, this series Fourier transforms the visibility samples to obtain the dirty image. To accelerate the process, we can use FFT algorithm rather than naive discrete Fourier transform. In Lab 4, we will use fast Fourier transform algorithms to obtain the dirty image from a sample radio interferometry data. It should be mentioned that dirty images, because of using a non-complete coverage of UV plane, are blurred. We can obtain a clean image with higher quality by processing the dirty beam. Dirty beam can be mathematically extracted from the dirty image formula. In this module, we don't go through the details of this process. However, in Lab 4, we will practically calculate the dirty beam associated with the dirty image. To learn how to create clean sky images using the associated dirty images of a target, you can study an algorithm named HugBeam Clean. Okay, that's all for today. Thanks for watching this video.